All right, well, good morning, afternoon, night, and evening, whenever you're watching this video. This is Mr. Lowry. Yes, this is my voice. I have to apologize. My voice is a bit scratchy right now. It's been trying to go in and out, but I'm going to do my best to guide you through the support necessary to be able to write an nth term definition. Now, when you look at other resources, you may not see the phrase nth term. You may see the phrase closed formula, or you may see explicit function. Things of that nature basically mean the same thing. We're trying to write a function to where, regardless of what the input is, that we can create an equation so that all we need to know are a couple of things different than the recursive definition that you are very comfortable with at this point. So one of the questions you may ask is, what must I know to be able to make this nth term definition? And what you find out is that it's almost real similar to what you need to know for the recursive rule. So one thing you need to know is your starting output. You need to know what is that first output, the first answer you get, understanding the first result you have, whatever the case may be. But it's the first output, not your first input. The second thing you need to know is, what is the pattern? This also can be identified as, what is the sequence? And so you need to understand, are you looking at geometric? Are you looking at arithmetic? How is it formulated? Is it adding or subtracting? Is it multiplying, dividing? Because depending on which structure you get will determine, depending on what pattern you get or sequence you get will determine what structure of your nth term definition you need to write. And then what will help with the domain portion is knowing your starting input. Now, this will just help you to be able to write that ending part that goes with your definition. So once again, the things you need to find is your starting output, understanding what your pattern or your sequence is, and also being able to state your starting input. So let's go through an example just so you are clear in understanding what I'm trying to communicate. So we have this given table here. We have the inputs, which are identified as the x's, and we have the outputs that are identified as t of x. Now don't get alarmed, t of x doesn't just stand for Texas. What it stands for is the name of the function we're going to write. Now, when we look at this, we see our inputs go by 1, and we look at our outputs, and we notice we go from 10 to 13, 13 to 16, 16 to 19, and 19 to 22. So take a moment and think about this. How are you getting from 10 to 13 that you can also do to get from 13 to 16, 16 to 19, and 19 to 22? Hopefully at this point you are recognizing that you are adding 3 every time. So remember 3 things I talked about. Our starting output. Our starting output is the number 10. Now in class you will notice that we write this traditionally as t of 0 is equal to 10, especially with recursive. I'm going to come back to that later and show you how that relates to our nth term. The second thing we need to notate is, what is our pattern or sequence? So in this pattern, we're adding 3 every time. That does tell us that this is arithmetic. So that will matter in our structure. So let's talk about the structure now, just so we don't lose sight of our ultimate goal here. So since this is arithmetic, then the thing is, our structure will fit something closer to being a linear equation. So something that looks like the family of y equals mx plus b, even though we don't use those letters. So for this problem, the name of the function is t of x, so we're going to honor that as such. Now, what we do know is the number we start with. The first answer is a 10. So that is where that t of 0 lives now. What we also know is that our pattern is plus 3. But what we have to recognize is that that plus 3 happens repeatedly. So anytime you have repetitive addition, it's the same as having multiplication. So this will be 3 times x. So that's how our sequence or our pattern fits this equation. But we need to state when we start to do this equation. This is where that 0 or that first input comes in. Because now we say that this function works as long as our input, which we said was x, is either greater than or equal to 0. And this, sports fans, is the nth term definition we were looking for. Now, when you look at this table for some, you may say, well, I don't understand that fully, but I do understand if we wrote this as a recursive rule. So let me go ahead and kind of clear the board so that we're able to see it as a recursive rule. The wonderful technology trick here. So once again, I mentioned how a lot of students, and even you including, I noticed that you are very strong in recursive definition. So from the same table, I can create the recursive definition. Now that will look like the following, and I'm going to speed this up a little bit because I understand you're very strong in this. So we would say the recursive definition would be t of 0 is equal to 10. Then we would say t of x is equal to t of x minus 1. And we notice we say plus 3. But we would say we would do that rule when x is greater than or equal to 1. So if you recall, we talked about how the first case doesn't change. But the second case always starts the next step and then onward. So if I look at this from a recursive definition first and turn it into the nth term, or like I mentioned earlier, the explicit form or the closed form, the information I need is actually inside of this recursive definition. So I'm going to use the green to show the recursive, the explicit definition or nth term definition. So we're still going to call this t of x. Now, this is 10 here. Once again, that's what starts off my rule. And for the majority of people's work I've seen, you don't have any issues with that. But if we look at it from the recursive, we actually can pull something out of it that may make it a lot easier for us to get to the end. Because our pattern of plus 3 is right there in our face. So like if we're going to look for the next answer from 10, we would add 3. If we're looking from there, after that, we will get a plus 3 again, plus 3 again, and a plus 3 again. So we are repetitively adding 3, which is why you see us say, well, then it's going to be 10 plus 3 times x. But we want to kind of bring in the 0 and the 1 at the same time. And that's why at the end we say x is greater than or equal to 0. Because this is setting us up to be able to handle either case that we have here. So that is an example of writing it from the nth term or into the nth term from recursive, even from the table. And I would say if you want to go back and look at how we handled it, definitely feel free to rewind the video to be able to pick up and slow it down and definitely bring questions to your Algebra 2 teacher. I want to go through one more example just to land this plane on today. Because the example that I've used originally was Aramaic. But what about if the pattern that I see is geometric? What do I do then? Well, let's start off first with the recursive definition. We'll just make one up to make sense. Okay, so let's call this S of P, excuse me, we're doing recursive. We'll try it again. So S of 0 is equal to, we'll say 19. And then we'll say S of P is equal to S of P minus 1. And we'll say times 5. But we got to say we do that when P is greater than or equal to 1. Now, as a reminder, I just made that one up. So now out of this, how do I write the nth term? Well, we still got to get the same piece of information. So I'm starting with the 19. So S of P is equal to 19. And that's my first output. The pattern or the sequence is geometric, but I'm multiplying by 3, or by 5, excuse me. So since I'm multiplying by 5, I show that. But what happens is I would do that again and again and again to be able to find my results. So since I have that repetitive multiplication, I want to write the 5 to the nth, or in this case, to the p power. But I gotta start, when do I start to do that? And it will be when p is greater than or equal to 0 in this case, because that allows for us to have the case 0 in here, as well as the cases where I'm moving on. So this would be my answer. This would be the nth term for this particular rule. Now, once again, you can definitely rewind the video to kind of see how I handle that portion. So there's one more thing I want to talk about on today in this video. And that is, what if we have a situation where the first input is not 0, but it's something else? Here's how we handle it. And I'm going to go ahead and use the same case that I just did to point out how we will handle it. So we have S of 1 equals 19, and S of P is equal to S of P minus 1. We'll still keep it times 5 when P is greater than or equal to 2. Now you will notice, if you look at the problem, my first input is at 1, so in recursive, the rest of the pattern starts at 2. Once again, you've shown yourself to be very strong in that, so I'm not going to rehash that part. But how does that affect my nth term definition or my explicit term? It slightly does, but the heart of it is still there. So S of P would still start with the number 19. It's not going to change. I would still have my pattern be multiplied by 5. It's right here. Now, here's what gets interesting. I am going to do repetitive multiplication. So I do have this to the nth power. But I don't have a 0 case, if you will, because this 19 is connected to the input of 1. So if I were to say when n is greater or equal to 0, I don't have a 0 case to base off of. It would be nice, but 0 isn't the input that goes with. The input it goes with is a 1. Okay? But if I put 1 in here, I will get 19 times 5 to the first, which is 19 times 5, which is definitely not 19. So I have a bit of a dilemma here. So the way to fix it, if your first input is not 0, then the n should reflect that up here. So instead of it being 5 to the nth power, it'll be 5 to the n minus 1 power. And now if I put 1 in here, I would get 19 times 5 to the 1 minus 1, which is 19 times 5 to the 0, which then, based on exponent rules that we know and love, 19 times 1, which does give us 19. So that's a slight adjustment we will have to make sure we lock this in. Okay. So as I wrap up this video, one last reminder of what you need. You need to have your starting output, whether it's from your table, whether it's from your graph, whether it's from the situation and words. Also be able to talk about what is your pattern in your sequence. And last but not least, have that starting input, because that's really going to help you when we start talking about the domain conversation. Okay? Hopefully this video has been helpful. Definitely reach out to your Algebra 2 teacher if you need more assistance. Otherwise, have a wonderful day.